Hi, my name is Casey Joyce, and I'm going to do a presentation on Physics Lab 4. This lab discussed what would happen with different spring forces. We had a mass attached to a spring that was a distance of 0.7 meters. In this, we collected position data to find predictions of the spring, the mass on the spring's position, and then took those positions to figure out the energy transfers that happened in the system. The energy system was found to be zero, and the positions that were predicted were similar to the actual experiment. This is my tracker data. To calibrate the system, we set the distance of the spring, which would be this line right here, to 0.7 meters. This mass is 0.402 kilograms. We started the tracker video right as the mass was released, as you can see here. The mass was released on the 5th frame, and this mass continued to move on the spring in the X and Y direction, making oscillations like this as it went. These oscillations made a big difference in the calculations that we'll find. Okay. The axis was set at a fixed point, and then it was calibrated, and that's how this data was found. These are the fundamental concepts that were used. The total force, or Newton's second law. In this case, F net is equal to the force of the spring and the force of the earth. The force of the earth is calculated times multiplying the mass times the gravity constant. The force of the spring equals the stiffness constant, which is K, times the length minus the relaxed length. To find this, we looked at the equation for the period. The period, or oscillations, is equal to T equals pi times 2 times the square root of the mass divided by the K, the spring stiffness. This was calculated by looking at our graphs calculated from Tracker. We look at the Y data, and we see at an entire period, which is from there to there, it was about 1.52 seconds. By finding the average, the period was 1.52 seconds throughout the Y values. This was plugged into the equation to find the spring constant, which is found to be 6.83 newtons per meter. Then we know that the force of the earth is equal to the force of the spring, due to the fact that the force of the earth was zero. This is because there's a very negligible mass. Because the force of the earth is equal to the force of the spring, you can derive an equation to end up equaling the relaxed length equals the length minus the mass times gravity divided by K. This was calculated to find the relaxed length was 1.23 meters. These are the main equations used, at least for the spring and the force values. We then had to put this into our code. We changed the code by, of course, changing the mass and the position, which was found to start at negative 0.634 y, and the others were 0. We made a .csv file, which I could not get to come up with my code, but in theory, it would have all your data from the tracker, and that's what it would make your model. You plug in the values that I just showed you how to calculate, and then for the equations, you would do length, which is just the spring position would be 0, 0 at the top, minus the ball position. And then L hat would be that length divided by the magnitude. K, now we can talk about the energy. You have to look at 3 different parts to find the energy. The kinetic energy, the universal gravity, and the universal spring. The system is made up of the mass, the spring, and the earth. Because the mass is so small, it's found that the kinetic energy and the universal gravity is equal to almost 0. Therefore, there is no change in energy. This means that there is 0 work being done on the system. There's no transfer of energy going in or out. This made it easier to calculate because you could set the delta E equal to 0. You plug in the equations into the code by the K being 1/2 mv squared, UG being mass times gravity times the position, looking at the Y, and the universal spring is the 1/2 times the K constant times the distance squared. This then would have been plotted, and a module would run that has 2 arrows, one going down, which shows the force of the spring, and one arrow pointing up, which would show the force of the gravity. Like I explained earlier, I could not get the CSV file to come up, but that's what it would look like. They would even out because the energy is equal to 0. There are changes in an oscillation if you look at either the X graph or the Y graph. From Tracker you can see here, we use data from the Y, but you can see if I change this to the X component, the oscillation or period would be a little different. The period for the X is 1.52, which is a little, the period for X is 1.65, which is slightly larger than the period for Y. This is because a larger period would mean that there is more change in distance when looking at the X per timestamp. This would mean that in the tracker video, the object is moving further in one set of time in the X direction than the Y. With the total energy equaling to 0, and the equations that you would add up, the kinetic energy plus the universal gravity plus the universal spring would prove this to correct. This was the data found for Lab 4. Thank you.